Okay, section 2.2. We're going to start section 2.2. I needed to get this part out of it first before we go on to the next part. It's not that long, but it's crucial that you separate between those because we need to get a few things out of the way. So they define f prime of x to be the limit as h approaches 0 of f of x minus f of x plus h minus f of x over h. And if you remember, this we did with a. So now we want to look at problem number 2 on page 125. So use the graph of f of x. There's f of x. To estimate each derivative, let's sketch the derivative. So I'm trying to kind of visualize at 0, there's 0. If I graph at 0 a tangent line, so this is kind of like approximation. What do you think the slope of that line is? Now, this is a slope of 1. A slope of 2, you guys, would be rise 2, run 1. Do you see how much? Oh boy, that looks horrible. Do you see how steeper that is? And slope of a half, you rise 1 and you run 2. So approximately, I'm gonna say this is about 2 or 3. Let's say 2. So at 0, I am at 2 right there, right? And so I'm assuming this is a 2. At 1, if I go to 1 and I draw a tangent line, that looks like a 0. So at 1, I am at 0. I try to line this up properly. So let's say this is 1. You are at 0. And if I go to 2, at 2, what do you think the slope of that line is? I could say negative 1. At 2, I am at negative 1. F prime at 3. Okay, a bit less than 1. You could say roughly 1, about, a bit steeper. I'll say it's about a 1. Maybe a bit less. A bit. And how about at 4? Do you see this is definitely less than? So if we said this is, oh, I'm sorry. Negative. This is like negative 1/2 maybe at 4. And how about at 5? At 5, it's leveling off. This is maybe like, I don't know, negative 1/4. And how about at 6? At 6, it looks like a 0, about a 0. And how about at 7? At 7, it looks to be maybe a half, maybe. And if you connect those with a smooth curve, that's pretty much what we want. Something like, oh, that wasn't here. That was actually here. So if I connect this with it's kind of like a thicker marker, because these are approximations, it doesn't have to be exact. That graph looks something like this. And that's pretty much all you have to do here. Now some notation for a derivative. Sir Newton decided to call a derivative f prime or y prime. Leibniz, German. Leibniz. And this turns out to be the most useful. These are different operators in different classes. This is differential equations. This is in this class. So let's see how this works. So they want us to find a derivative evaluated at 0, 1/2, 1, 2, and 3. Well, we have a couple of options. We could actually do the work. We could say f prime of 0 is the limit as h approaches 0 of f of 0 plus h minus f of 0 over h. And we could do it for a half, put 1/2 there, put 1/2 there, and put 1/2 there. We could do it for 1, but that's a lot of work. Instead, here's an idea. Why don't we find the derivative at any x, which is the definition in this section, and it's right there. F of x plus h minus f of x all over h. And if I do that, then guess what? Once I find a derivative in terms of x, let x equal 0 in there, let x equal 1/2, x equal 1, x equal 2, and I can do this as many times as it takes. So f prime of x would be the limit as h approaches 0. F of x plus h is x plus h cubed, minus f of x is x cubed over h. That is the limit as h approaches 0 of x cubed plus 3x squared h plus 3x h squared plus h cubed minus x cubed all over h. Those cancel out, and I'm left with the limit as h approaches 0. If I factor an h out of the top, and I could say f prime of x equal the limit as h approaches 0 of 3x squared plus 3xh plus h squared. If I replace h by 0, I will get f prime of x to equal 3x squared. This is the derivative of x cubed at any given value of x. At 0, f prime of 0 is simply 3 times 0 squared, which is 0. F prime at 1/2, it's 3 times 1/2 squared, that's 3/4. F prime at 2 is 3 times 2 squared, that's 12. And f prime at 3 is 3 times 3 squared, which is 27. And by doing this, I saved myself all of this work. So we're going to stop here. This is the homework. I needed to finish this homework before we get to the next portion of this section.